Unit 3, pages 49 and 57, the mole concept. In everyday life, we count things like eggs with simple integers, 1, 2, 3, 4. For larger quantities, the counting might be done in dozens or gross. To convert between counting schemes, a conversion factor is used. For example, 12 eggs is also represented as 1 dozen. So how many dozen are in 6 eggs? Well, you have half a dozen. How many eggs are in 2 dozen? 2 dozen is going to be 2 times 12, 24 eggs. So for atoms and molecules, we use a similar method, but instead of counting by dozens, we use a much larger group of things called a mole. So Avogadro's number is 6.022 to the 10 to the 23rd and is represented with capital N sub A, Avogadro's number. This is Avogadro's number, and it's going to be the amount of things per mole. So this could be the number of atoms per mole, the number of molecules per mole, the number of cations per mole, anions per mole, pretty much anything per mole. So what's a mole? It's the same idea as a dozen, but instead of 12 things, there are Avogadro's number of things for every 1 mole. So it's like saying 1 dozen equals 12 things, or 1 mole equals 6.022 to the 10 to the 23rd things. So consider 2 samples of CO2. 1 dozen molecules would have 12 CO2 molecules, 12 carbon atoms. 2 times 12 is 24 oxygen atoms, and 3 times 12 is 36 total atoms. If you had 1 mole of the molecules, you would have 6.02 to the 10 to the 23rd molecules, 6.02 to the 10 to the 23rd carbons, 2 times 6.02 to the 10 to the 23rd oxygen atoms, and a total of 1, 2, 3 times 6.02 to the 10 to the 23rd atoms. Molar mass is the mass of 1 mole of molecules, and to find the molar mass, you add up the atomic masses of each element. Remember, the average mass on the periodic table is also going to be the molar mass of that element. So here, I want to take the molar mass of each of these elements, multiply them times their subscripts, and add them together to get the total mass of this entire molecule. So the carbon has a mass of 12.01, and you're going to multiply that times 12 carbon atoms. We're going to add that to my hydrogens. There's a mass of 1.01 for each hydrogen times there are 22 of them. And we have oxygen, which has a mass of 16 times 11 oxygens. And so when I do this math, I will obtain the molar mass of this compound up here. Note that you can type all of this into your calculator at one time, so you don't really have to do this on paper. You can just get molar masses in your calculator. 12.01 times 12 carbon atoms plus 1.01 times 22 hydrogens plus 16 times 11 oxygens gives us a molar mass of 342.34 grams per mole for the entire C12H22O11 molecule. Formula mass is the same idea as molar mass, but is used for empirical formulas. Recall that table salt, or NaCl, is not a single molecule, but exists instead as a crystal containing many atoms. The mass of 1 mole of the formula NaCl does not represent the mass of a mole of actual molecules. There are no single NaCl molecules. Instead, the mass represents the mass of 1 empirical formula unit that is written as NaCl. So, exercise 3.13, what is the formula mass of magnesium nitrate? We have 1 magnesium, which has a mass of 24.31 on the periodic table, so times 1 to be technical, plus we have nitrogen, who has a mass of 14.01, times this 2 distributes only into the parentheses, and so we have times 2 nitrogens, plus oxygen has a mass of 16, times 2 times 3 is 6 oxygens. And so when we do this math, we get 148.33 grams per mole. Working in AMU, recall that the masses in the periodic table also represent the mass of 1 atom in AMU, instead of a mole of atoms. The formula mass and molar mass can also be obtained in AMU by using atomic masses in atomic mass unit. The result will have the unit, atomic mass units per molecule. In other words, the formula mass of magnesium nitrate is not only 148.29 grams per mole, but it can also be atomic mass units per molecule. The carbon-12 scale Atomic masses found in the periodic table are measured against a standard using the isotope carbon-12. Atomic mass is defined as 12.0000 grams is equal to 1 mole of carbon atoms, or 12 AMU equals 1 carbon atom. Both the unit of gram and AMU are defined in this way. Percent composition. The percent composition by mass is calculated in the same way any percent is calculated. The percent by mass of carbon in the molecule C12H22O11 is going to be the mass of all the carbons here. So it's going to be carbon's mass, which is 12, times the fact that you have 12 carbons, so 12 times the mass of carbon, which is 12.01, divided by the total mass of your molecule, which is 342 grams per mole. And so when you divide these values times 100, you get a percentage. 42% of this molecule is made up of carbon. Recall that the formula mass, 342 grams per mole, was calculated above. Also, keep in mind that when you add together the percentages of carbon, hydrogen, and oxygen in this molecule, it should add up to a total of 100%. Converting between mass and moles. Formula mass, or molar mass, and Avogadro's number are key conversion factors in the calculations. And so here you can convert from grams to moles by taking the grams you're given and dividing by the formula mass or molar mass from the periodic table, and that's going to give you moles. In reverse, you would take moles times the formula mass, and that would give you grams. So exercise 3.14. How many moles are in a 15.0 gram sample of CO2? So we take 15.0 grams of CO2 times, draw a line, and we're going to bring down grams of CO2, and we can go to 1 mole of CO2 as long as we get the molar mass from the periodic table for CO2, which is going to be 44 when you add up 1 carbon plus 2 oxygens. So all I have to do here is 15 divided by 44, and that gives me 0.34 moles of CO2. So that was exercise 3.14. 3.15 asks for the reverse. How many grams of CO2 are required to have 0.5 moles? So I would take 0.5 moles of CO2 times, draw a line, bring down moles of CO2, and in 1 mole there are 44 grams of CO2 from the periodic table, molar mass. And so I would do 0.5 times 44, which would give me 22 grams of CO2. So moles to particles, if you have a thing, such as molecules, atoms, eggs, cations, anions, total atoms, etc., then you would have 6.022 times 10 to the 23rd of those things equal to 1 mole. So you would take that thing, however much you have, divided by Avogadro's number, and you would get moles, or take moles times Avogadro's number, and you would get how many things you have present. So exercise 3.16, how many oxygen atoms are in 0.7 moles sample of CO2? We have to be careful because we're given 0.7 moles of CO2 times, draw a line, if I bring down moles of CO2, this, and I can't put atoms of CO2 up here because that's not what I'm being asked for. I'm asked for atoms of just the oxygen. So what I want to do here is a mole to mole ratio from CO2 to just O. And because if I have 1 mole of CO2, since there are 2 atoms of oxygens here, that means I have 2 moles worth of oxygens for every 1 mole's worth of CO2. Now I can bring down 1 mole of oxygen, and I want to know how many atoms, which means I want to use Avogadro's number, 6.022 times 10 to the 23rd atoms of oxygen, in order to get my answer. And when you do this calculation, 0.7 times 2 times 6.022 times 10 to the 23rd, you get 4.21 times 10 to the 23rd oxygen atoms. Another way to do the same calculation would be to say 0.7 moles of CO2 times, draw a line, and 1 mole of CO2 is equal to 6.022 times 10 to the 23rd molecules of CO2. And so you could convert to Avogadro's number here, but recognize that we still want to know how many atoms of oxygen. So in 1 molecule of CO2, there are 2 oxygen atoms present. And so here you would do the same calculation, 0.7 times Avogadro's number times 2, which gets you the same final answer. Exercise 3.17, a sample of CO2 contains 8.43 times 10 to the 23rd CO2 molecules. How many moles of CO2 is this? So we'll take 8.43 times 10 to the 23rd molecules of CO2 times, draw a line, and to get from molecules of CO2 to 1 mole of CO2, I just use Avogadro's number. 6.022 times 10 to the 23rd molecules equals 1 mole of CO2, and then multiply, 8.43 times 10 to the 23rd, I'm going to put it in parentheses, and then hit divided by, open parentheses, 6.022 times 10 to the 23rd, and this will give me 1.4 moles of CO2. You're going to want to be careful when you're using this type of calculator and use parentheses. Better to use than not. Exercise 3.18. A sample of CO2 contains 8.43 times 10 to the 23rd oxygen atoms. What is the mass of the CO2 sample? So we want to know grams of CO2, but we're given the amount of oxygen atoms. So there's two ways to do this problem. 8.43 times 10 to the 23rd oxygen atoms times, draw a line, bring down oxygen atoms, and we have Avogadro's number of oxygen atoms per 1 mole of oxygen times, draw a line. And then you could do a mole-to-mole ratio from moles of oxygen to moles of CO2, because in 1 mole's worth of CO2 there are 2 moles of oxygen. And then from here I can go from moles of CO2 to the molar mass from the periodic table, which is 44, in order to calculate my final answer, which is 30.8 grams of CO2. The other way to do the same problem would be to say 8.43 times 10 to the 23rd oxygen atoms, bring down oxygen atoms, and then here you can say there are 2 oxygen atoms in 1 molecule of CO2, and then we could say molecules of CO2 converts to 1 mole of CO2 when you use Avogadro's number, and then 1 mole of CO2 converts to mass by using the molar mass from the periodic table. Notice that we're still doing the same type of math, division and multiplication, and you should end up with the same answer, 30.8 grams of CO2. Here's the note card for this section. So here's kind of our general roadmap that 1 mole can be converted to molar mass by using the formula mass on the periodic table, and that's going to be equal grams per 1 mole. Or you can use Avogadro's number to convert to number of atoms, molecules, ions, etc., depending on what amount of things you're looking for. Percent composition is always going to be the part divided by the whole times 100, and be careful because if water is my whole, then 2 parts of that water is hydrogen, so you'd have to take the mass of hydrogen times 2 divided by the total mass of the water times 100 to get its percentage. This is known as composition stoichiometry, where you do a mole-to-mole ratio between 1 mole of the entire compound to moles of just one element in that compound. And so because there are 8 hydrogens here, I would say that 1 mole of ammonium sulfide contains 8 moles of hydrogen, or you can take the inverse of that depending on how your dimensional analysis gets set up. So pay close attention to what's being given and what you're asked to find. So if you're given grams of NH3 but asked to find atoms of hydrogen, then you're going to have to do that composition stoichiometry step here, whether you do it this way or you do it with the whole molecule to atoms method shown in the sample problems.